Welcome to my channel, viewers. We are discussing lesson number 10, class 10 series CBC curriculum. This is about tangent to a circle and its properties. Now let us recall chord which you discussed earlier. What is a chord? You imagine 2 points on this circle, say A and B, right? Then you join AB. So you got a chord. It's a line segment joining any 2 points on the circumference of the circle, right? Now let us extend this chord on both sides. If you extend this chord on both sides, right? Let us extend this chord on both sides. So this line is called secant. So secant is a line which intersects a circle into distinct points, right? This line L is a secant. It is intersecting the circle into distinct points A and B. And the part of the secant contained by the circle is called chord. This line L intersect the circle into distinct points A and B. The part of the secant contained by the circle is AB. AB is within the circle. It is called chord. Now let us make this secant through the center of the circle. So this time you got the longest chord. CD is the longest chord. Diameter. CD is called diameter. Diameter is the longest chord. So when you made the secant through the center of the circle, then you got the longest chord. Now let us come down. Let us go away from the center of the circle. You are going away from the center of the circle. This is even far away from the center of the circle. And so on. You make seconds away from the center of the circle. So at one point of time, you will find that this line will only touch the circle at one point. Say this is line N. Now in case of line N, you see it only touched the circle only one point. This line is called tangent to the circle. So tangent means it's a line which touches the circle in one point, and that point is called point of contact. So it is point P. So the line N touches the circle at point P. The point P is called point of contact, or it is called touch. So tangent is a line which touches the circle only in one point. That is, there is only one common point in between a tangent and a circle. The point P is the common point between line N and the circle. Now, if you make a line through the radius, through the center of the circle, through the point of contact, let us make this line. This is suppose line M, and this line is called normal. This is called normal. So normal is the line which is made through the center of the circle and the point of contact of the tangent. This is called normal. Next, we will prove that tangent is perpendicular to the normal. That means the line joining radius and the point of contact of the tangent is perpendicular to the tangent. That means this angle is 90 degree. Right? So this is center of the circle, and you make one tangent here. This is one tangent. This is point of contact P. This is center of the circle, and you join this line. This angle is called, this angle is a right angle. That means tangent makes right angle with the radius of the circle at the point of contact. Now let us prove this property. The tangent at any point of a circle is perpendicular to the radius through the point of contact. So let us make a tangent. Let us take one point on this circle and you make a tangent here. This is line L. Now point of contact is P. Let us join center of the circle with P, right? So line L is a tangent to the circle, and P is the point of contact. P is the point of contact. P is joined with center C. Suppose this is C, center C. Now we have to prove that. To prove CP perpendicular to L, right? So we have to show that tangent at any point of a circle is perpendicular to the radius through the point of contact. Through the point of contact means through the point P. So we have to prove that PC is perpendicular to L, this line L. Now let's take some point, say this is Q, this is R, this is suppose S. Now let us join CP, CQ, CR and CS. So we are taking a few more points on the line L. So let us take a few more points. Q, R, S on L, right? And CQ, CR, CS are joined. These are joined. Now you remember the definition of perpendicular on a line from an external point. What is meant by perpendicular on a line from an external point? Say this is line L and you are taking an external point, suppose this is P. So what is meant by perpendicular from P on this line L? Perpendicular from an external point on a line means the shortest distance between the line and the point P. So this is the shortest distance perpendicular. If you take these points, suppose PQ and PR, you see PQ is longer than PM, PR is also longer than PM, right? So PM is the shortest distance. Shortest distance is called perpendicular. So when we say perpendicular from an external point to a given line, that means it is the shortest distance between a point and a line. Now we'll try to show that CP is the shortest distance between the line L and C. That is why we are trying to prove that the other line segments like CQ, CR, CH, CS, etc. are longer than CP. So let's take point QRS, etc. on line L. We are joining CQ, CR, CS, right? Now we see point P is on the circle, Q, R, S, etc. are outside the circle, outside the given circle, right? Therefore, CQ, it is greater than CP, CR, it is greater than CP, CS greater than CP, etc. In fact, we can say CS is greater than CR, it is greater than CQ, it is greater than CP, right? That means among these line segments, you see CP is the shortest because point P is on the circle and other points Q, R, S, etc. are outside the circle. So CP is the shortest line segment here. That is, CP is the shortest line segment. Therefore, CP perpendicular to L. You have to mention here the shortest distance from an external point to a given line is the perpendicular to the line, right? So CP is perpendicular to the line L, as because CP is, you find CP is the shortest distance. Other points Q, R, S, if you take some other points on this line L, you find that all other points will be outside the circle. Only the point P is on the circle. So obviously CP is the shortest. So the shortest distance from an external point to a given line is the perpendicular to the line. So we call CP is perpendicular to L. Now let us try to prove another theorem here. At any point on a circle, there can be only one tangent. So let us take point P, suppose here. Let us draw a tangent through the point P at the point of contact P. This is tangent. Say this line is L, right? This is the center of the circle. So at any point on a circle, there can be only one and one tangent. So line L is tangent to the given circle at point P. That is, P is the point of contact, right? This line touches the circle at point P. To prove there can be only one tangent through P. So we have to prove that there can be only one tangent through the point of contact P. Right? Now let's make one more tangent. Say there is one more line through P which is also tangent. This is just imagination. We are assuming that there is one more line M. Say it is also tangent to the given circle. So it's our assumption. So let's say line M is also tangent to the circle at P. So we are assuming that there are two tangents, line L and line M, and they are touching the given circle at point P. Right? Now, in the earlier theorem, we proved that tangent is perpendicular to the radius at the point of contact. Right? So we say CP is perpendicular to L. Why? Tangent is perpendicular to the radius at the point of contact. Okay, this we proved earlier theorem. Tangent is perpendicular to the radius at the point of contact. So this angle is 90 degree. Say this is point A and you are taking point, say it is B on line M. So CP is perpendicular to L. That means CP perpendicular to PA. Right? So this gives angle CPA equal to 90 degree. Similarly, line M is also tangent at P. That we are assuming here. No? Line M is also tangent to the circle at P. This was our assumption, right? So line M is also tangent to the circle at point P. That means CP perpendicular to line M, or you can say that is CP perpendicular to PB, or you can say angle CPB equal to 90 degree. Same property. Tangent is perpendicular to the radius at the point of contact. So let's take this is 1 and this is 2, suppose. Now from 1 and 2, you can say angle CPA equal to angle CPB, both 90 degree. So we can compare them, CPA equal to CPB. Now from figure you see CPA and CPB, are they equal? No. You see CPB is greater than CPA, but from figure, but it is clear that angle CPB greater than angle CPA, right? This angle CPB, this angle is greater than CPA from the figure. So we got one incorrect conclusion. If we assume that there is one more tangent at the point P, if we assume that line M is also tangent to the given circle at point P, then we got one incorrect conclusion. What is incorrect? CPA equal to CPB. It is next to impossible. It is impossible, right? Because angle CPB is greater than CPA. It is clear. These two are distinct lines, so these two angles cannot be equal. C, P, A, B. So this angle is smaller than this angle, right? CPB is greater than CPA. So our assumption is incorrect. Therefore, our assumption was wrong. That is, line M cannot be a tangent at P. Our assumption was line M is also a tangent to the circle at point P. So we now find that assumption is wrong. Line M cannot be a tangent to the circle at point P. That is, there can be only one tangent to a given circle at one point. Right? So to the given circle, there can be only one tangent at one point on the circle. We cannot draw more than one tangent. So thank you for viewers for watching this video. Based on these two theorems, we'll discuss a few sums in the next video. Keep in touch.